Okay, so today I'm going to expand on our understanding of probability by specifically looking at what is known as continuous probability. So specifically, these are referred to as continuous random variables, much like how we have discrete random variables. What goes on with continuous random variables is that the quantity that you're looking at could take any arbitrary level of accuracy. Like, for example, if we measure the length of an object, it could be written as 1 meter long. But if you're more accurate in your measurement, maybe it's actually closer to 1.1 meters. That would make it accurate to a single decimal place. Or if you had state-of-the-art equipment, you would find that the length could be any number of decimal places. The limit to our accuracy is purely based on our own ability to measure the thing rather than the thing itself. It could be any arbitrary level of accuracy. So lengths are pretty common for continuous quantities. Other things like height, weight, time, volume, area, all these things that are like physical things in the real world don't have neat values that could be fit into. As far as how you model this kind of probability, how you actually solve these kinds of things, what you typically do is use what's known as probability density functions. So what we do is we create some sort of function which describes the overall probability of any given event occurring. And so since we're using functions, what ends up being the case is that you get some sort of piecewise thing. You'll have a function defined over a particular domain. And the way it works is that the area under a curve is the probability that your result occurs within any given domain. So for example, if you want to know the probability that your event could be anywhere between A and B, then you would have to do the definite integral over that domain, because that's how you find area under any curve. Now, it won't always be the case that you need to do integrals. If your probability density function is sufficiently easy that it makes like a square or a trapezium or a triangle or some other area that's super easy to calculate, then by all means go ahead and use geometry for that. But for the vast majority of the cases it will look at, you would be using the definite integral to find the area under a curve. So if we have a look at one particular possibility, you've got, this is your piecewise function. Usually it's just like you have a function and then 0 for everywhere else. So it's kind of a piecewise. Really, it's just sketch a function over a domain, but this is just how they typically look. And so what it ends up meaning is the area under the curve is what the probability is. So this quantity, whatever it happens to be, could be any value between 0 and 6. Right? It could be anywhere in between that. And so if you want to find like a particular range of probabilities, like let's say you want to figure out where the likelihood that your value occurs between 2 and 4, you're just doing definite integral from 2 to 4. So you slap that together, and then, well, this is just definite integral now. So you antidiff the cosine to become the sine. And then you do capital F of top minus capital F of bottom, simplify, and you get your probability. So that's fundamentals as far as how we find probabilities. Fair enough so far on that? Any questions yet? All good. Is that a thumbs up for a question or a thumbs up for all good? I know you just recently joined. All good. Okay. So one thing I skipped at the beginning was that because probability density functions, the area of it tells you the probability of any given event occurring, it goes to show that, or it follows that the total area under a curve must therefore be equal to 1. Because if it was anything more, then you suddenly have a scenario where you have more than 100% probability in a given scenario. So if you ever want to prove that you have a probability density function, then you want to prove that the area under the curve is equal to 1. There's a bit more to it than just that, but that's what it ends up being in the vast majority of cases. You just want to prove the area under it is 1. And so again, if you want to prove the area under it is 1, then you do your definite integral over the full domain. So 0 to 6, sub in, equals 1, and so we're all sorted. The other criteria that doesn't really come up all that often is that your function has to be greater than or equal to 0 for the entire domain. And that's simply because, well, if it was below the x-axis, then that would be considered negative area and therefore negative probability. So very unlikely. I've never seen a function actually, or sorry, I've never seen a PDF dip below the x-axis, but it's worth putting it there just because it is technically a criteria. Sometimes not only we have to prove that a function is a PDF, probability density function, but you also have to solve for a value of k that makes it a PDF. And so the exact same situation is how you handle it. You do your definite integral from 1 to 2, anti-diffing whatever you have, and then subbing in the values. But instead of proving that it equals 1, you set it equal to 1 ahead of time, because you already want to make it a PDF, and so by definition the area has to be equal to 1. So if you let it equal 1, you just solve for k, nothing too crazy from there. Another less common version of this, a CAS version of this, is that they'll actually put the variable in the domain rather than in the function itself. And so once again, you want to prove this is a PDF, and so the integral over the full domain must equal 1. And so all it ends up meaning is that the variables that you have that are in here, they go in the top and bottom. So k plus 1, it's a CAS solve situation. You would never be able to really do this by hand, or at least not reasonably done by hand. This part here just sets your effective domain. The reason why that's important is because for cosine, because its circular function repeats more than once, this domain could repeat infinitely. And so it does need a specified restriction on it. Was that a question?
Yeah, could you hear me?
Yeah, I only hear you now.
Yeah, just wanted to ask, are you able, how would we actually solve that on CAS if you had to do it? Are you able to show us?
Oh yeah, like looking at what it actually means to plug it in. Yeah,
Yeah.
cool. So TI Inspire, if we go to the handwritten notes, it is just a CAS solve, at least initially it is. So for the solve menu, 3 for algebra, and then 1 for solve. And as far as getting the actual integral itself up, you've got a couple of different options. You could do a shift, then a plus, which will bring up the integral as a shortcut. Or if you don't memorize that, it's in the calculus menu down here as integral. Both of which will get you the required thing to put in there. And so all you do is you just write exactly what I wrote in the PDF. So k plus 1 cosine x plus 1 dx is equal to 1 comma k, since you're solving for the k value. And then as far as putting an effective domain on it, that's going to be control and then this equals symbol here. That's going to pop up this window. And then this vertical line is allowing you to set your domain. So again, pull that window up again so you can get those inequality symbols. And then, yeah, this was between 0 and 2. So what you're going to do is hit enter on that. It's going to give you the required value of k. If you don't have that, I believe it's just going to give you some generic possibility. And so be sure to put that in. So that's TI Inspire. As far as Casio goes, let's take a look. Very similar. Where's the button? There it is. So for Casio, get the keyboard open. And what are we doing? We're doing a solve, which I believe was math 3. And then integral, which is this one. Otherwise, it's the same stuff. So you can put, I mean, it'll be a bit of a pain to use specifically k here when you've got x, y, and z. And so, well, yeah, like when you've got actual, does it matter? They are bold. I don't know how this one handles whether it's bold or whether it's not bold, so I wouldn't really trust it. Maybe I would just go and do what's going on here. So k plus 1, k. Do your circular function. So trig. Oh wait, no, it's not sine, is it? It's cos. Cos x plus 1 dx equals 1, comma k. Okay. And then as far as domain is sorted, go math 3, and it's the exact same button, that vertical line, pipe. 0 less than k less than, oh, where'd it go? And then that gives you the same result, but they just didn't put it over same denominator. It's just split between two separate stages. Anything to clarify further on those?
No, that's all good. Thanks.
Yep, easy. Okay. We did this one earlier, but I'll briefly touch on it just for the new arrivals. So if you want to find probability over a specific domain, you basically just set that as the boundaries of your integral. So instead of doing it over the full 0 to 6, you're now doing it from 2 to 4, and that gives you your target probability. Which means, anti-diff your function, sub in top and bottom, it's just doing definite integrals. Where you have to do a lower bound of an interval, that's kind of these kinds of questions, where you've got to figure out what this value of A is such that a probability is equal to a specific value. So you've got probability, you've got upper bound, even though it doesn't necessarily say it, and you need to figure out lower bound. The reason why you have upper bound is if you think about like x being greater than some value A, it's never going to get bigger than 15. It just 15 pi. Can't get any bigger than that. So that sets 15 pi as your upper bound for your domain, and A must therefore be a lower bound. So that sets the terminals. Function is function, nothing too crazy there. And the probability is going to be what it equals, since definite integral is probability. And so all you do again is, if you're doing this tech-free, then anti-diff, do capital F of top minus capital F of bottom, and sub in, well, yeah, it just means subbing in those values. That's going to get you to this line here. This one is fully solvable, although I guess we're doing a bit of rearranging before that. So yeah, multiply everything by 2 to get rid of some fractions. Oh, sorry, 4 to get rid of some fractions. This one, fully solvable, so sine 15 pi over 6. That sorts itself out. What is a bit harder to solve is this, because you've got an unknown inside of the circular function. So what we end up doing is kind of two separate versions of solving circular functions. One is where you have the angle, which gives you a value, and one is where you don't have, or at least you have a variable in the angle, in which case you rearrange to get that circular function on its own. You've got exact value, you've got circular function. You're now just looking for where does sine equal root 212, which is going to be pi over 4 and 3 pi over 4. I'm doing the general solution here just to sort of show all possibilities there. And in fact, that's probably what you would want to do for this as well. You'd want to actually get a general solution, because when you think about rearranging this to get A on its own, you've got to remember that A has to fit within this domain. And so if you just pick like the first solution that you get, it might not even fit. Like, let's see here. If you had n equals 0, then you would have pi over 4 or, sorry, no, if you choose n equals 0, you'd have 3 pi over 2 or 9 pi over 4, both of which are not going to fit into 9 pi. So worth pointing out that you're going to have to choose a specific iteration around the unit circle to actually fit your target domain, which in this case turns out to be the second iteration forward. So you sub in your n equals 1, simplify. This one's too big, this one fits nicely. Any questions around how that works? Conditional probability works the same way it always has. So you're always going to start by expanding out the conditional probability formula itself. And you're going to be looking out for like the keyword given. Usually it'll say something like given. And the way it works is the words immediately after the word probability is the thing on the left. So this means I want to find the probability that the task takes between 2 to 3 hours. That's what that means. The words immediately after given are the conditional. So given that the task took less than 4 hours, which is why you put that on the conditional side. Task is less than 4. And then, yeah, it just means you want the intersection of these two things divided by the conditional. As far as solving these intersections, figuring out what they actually are, if it's not immediately obvious how to read that, then drawing up a number line like this is pretty nice. So it just means you do this interval from 2 to 3, so that's that little bit there. You do this interval, everything less than 4, so that's that. And then the intersection is just where those two things overlap, which is why the whole thing just simplifies down to just saying between 2 and 3. And so yeah, that just means you need to solve each of these individual probabilities, and because it's a continuous probability, you solve them with integrals. So to get between 2 and 3, you just set your terminals as 2 and 3. To get less than 4, you set your terminals as 0 to 4, because the absolute lowest value in this one was 0. So you simplify all those down. There's your numerator, there's your denominator. Perform that division. I like using an actual division symbol. It tends to make the working out look a little bit easier to work with. And then, yeah, just condense it all down. Those are basically the fundamentals of how you calculate continuous probabilities. Anything to clarify in any of that before I move on to the statistics? Okay. So statistics are going to be kind of similar to what you might already be familiar with, although there will be at least, I think there's 2 new statistics that come up with the with continuous probability. But first we have the mean. So the mean will look kind of similar to at least a binomial, where you have just x f of x. So kind of like how you have NP, or you have x times each of the probabilities for discrete. It's the same sort of deal, because function is like your probability value and x is the outcome. So if you remember your discrete probability tables, it was like x times probability, x times probability. Same thing. Except, yeah, it's now integrals. So when you're after finding the mean, literally all you're doing is over whatever domain is given. So in this case, it's from 1 to 2. You take the function that you have and you slap an x out the front of it. That's it. So instead of just doing 2 over x squared, you now do x times 2 over x squared, which of course simplifies to 1 over x with the 2 out the front. And then you just antidiff that from there. Nothing too crazy. So very similar to what you do when calculating actual probabilities, x f of x. And this goes on your formula sheet, by the way. So even if you do somehow forget it, it'll be on the formula sheet. This has, yeah, why not? We'll talk about it briefly. This will only really be a book thing. This hasn't actually come up in any like exam sort of scenario. And so basically, if you have some sort of linear transformation on your expected value sort of situation, then you can use the exact same simplification that was mentioned when we were doing discrete. which is you can factor the A all the way out the front and you let the B as an addition outside. This is an actual factorization. There's a much more complicated proof that proves this is the case. Don't think that you can just take an A out the front and then call it a day. There's a complicated proof that gets from left to right. Okay, and so if you're doing that sort of simplification way, which is a lot easier, it just means take 2 out the front and then 3 out the other side, and then you just solve the mean like you always have, which is x f of x, and all you got to do is multiply by 2 and add 3 at the end. That's probably the simplest way of doing that sort of thing. If you do forget to use that, then the basic rule is whatever's happening in here, instead of putting x out the front of f of x, you put that out the front of f of x. That's basically it. Now, that can be challenging in the tech-free because sometimes the resulting function just isn't particularly solvable. Whereas if you do this sort of situation here by rearranging it, it should be, well, it's much more likely to be solvable. Because you can imagine when you do a product of linear and some other function, pretty unlikely to actually be able to do that by hand unless that other function is also some sort of power function. Like if this was a cosine, for instance, very hard to do the antidiff of that. Doable, but not by math method standards. So knowing this rearrangement is going to be pretty crucial if you're doing the textbook questions. Again, as I said, this doesn't actually come up in any SAC or exam I've ever seen. Now, I've ever seen, right? Your school may do something different, but that's why I'm covering it. Okay, so here's a new statistic, median, or otherwise known as a type of percentile. So the median is simply just the middle value of any given data set. It's a little bit different to the mean, which is the average of data set. So for instance, if I have the values 1, 2, and 100, the median of that is 2. Out of the 3 possible elements, the 2 is the middle value. Whereas the mean would be heavily skewed to the right because you've got this big number up here where you would do like, you do 1 plus 2 plus 100 all divided by 3. You get a much bigger number than if you had just done the middle value. So that's what median's all about. You're taking the smack dab middle of the distribution. So that should make sense that the median accounts for half the total probability, as far as how that works in probability density functions, because it's smack dab in the middle of your distribution. And what you want to find is what value of m would actually achieve that, which is why you set it as an upper bound of your integral rather than I guess you could kind of do a lower bound version of that, but it's not conventional to do it that way. As far as what it means as far as percentiles goes, median is just another word for the 50th percentile, which simply just means that, like if you consider like any percentile, the nth percentile just tells you some value that n% of values fall underneath. So like the 90th percentile would be something like, if I were to distribute that on a hand-drawn graph, it might be something like, so if we draw a little bell curve, it might be like this value here, which accounts for 90% of all the possible outcomes here. And so yeah, median, you just set that value to 50%. If you're doing any other percentile, you set it to whatever that percentile is. So 70th, you do 0.7, 90th, you would do 0.9, so on and so forth. We've technically done this before, but we've set our value, what was it? We've done it before in this. It's kind of a percentile, but we set an upper bound instead of a lower bound. Equals some value. Yeah. So it's the same overall way to solve it. but it just has a specific name now. And it's worded differently as well. So in this case, we're looking at a probability distribution for phone calls, and we want to find the value of A such that 90% of phone calls last less than A minutes. So if it's less than A minutes, you want A to be your upper bound, and whatever your lower bound is, you would set that from the domain. It's 90th percentile, so you're going to put 0.9 as your value, and then yeah, we already saw how this works. Anti-diff this, sub in A, sub in 0, expand, 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 expand. In this case, because you have an exponential involved, to get that A on its own, you have to convert to a equivalent logarithm. Rearrange, rearrange, rearrange. Gets you a possible, well, the value of A. And if you're tech active, then you can obviously just get the decimal version of that should you need it. This one doesn't say anything about that, so you would give the exact value, but a lot of these questions actually do ask for a specific value to some number decimal places, or even just like round it to the nearest whole number. Variance, you might slightly recognize the equation for it, kind of like how you do your x take mean squared multiplied by probability. Same thing, but for f of x. Worth pointing out, because the mean is one of the criteria for doing variance, I would highly recommend that you do these in two separate parts. One where you first find the mean itself, and then when you get that value, then you plug it into your variance equation. Worth again pointing out, this is on your formula sheet. You don't have to have this memorized. So let's say you want to do the variance of this equation. First up, set up the integral. So x minus mean all squared, and then you put the f of x in that spot. To get this mean value, you just go back to when we're doing e of x, which is just x times f of x. So instead of putting all this at the front of f, you just put x at the front of f. Over the same domain, we found this value earlier, so I'm just going to reuse the 2 natural log 2. So we take that, chuck it back into this spot, and this will always be Cas. Like, it's super unlikely for this to be anything other than Cas. You would have to have a very easy value for mean if it was tech active, or tech free rather, because like as soon as you expand this out, like that's squaring stuff. You really need another power function in here before it's actually doable by hand. So historically speaking, these are always Cas. This is once again just plugging in an integral though, so we've seen how that works for both TI Nspire and Casio. Any questions so far? Okay, variance of a function. I mean, we'll touch on the simplification version, but again, this is one of those things where you'll only use it for the book and nothing else, really. So if you have a linear sort of transformation, it just means you take the a out the front, square it, and this plus b just literally doesn't matter. So if you have to do, if you have to do variance of 2x plus 3, then you just take it at the front, make it 4, and then do variance like you're already used to doing. Do variance like you're used to doing, and then just multiply by 4 at the end. I won't touch more on that. There's no real point. Standard deviation, super easy as well. It's always just square root of variance. So if you know your variance equation, which you will, it'll be on your formula sheet. Literally all you do is you slap a square root at the end of it. So if we already found our variance before was that, then the standard deviation is just the square root of that. Worth pointing out, just because there's a negative on that logarithm doesn't necessarily mean that you can't take the square root. A negative on the logarithm doesn't even necessarily mean that the logarithm is a negative number. If we see what that actually ended up equaling, well, this is a slightly different one, but you can see negative 3 natural log 0.1 actually is a positive number. And so just because there's a negative there doesn't necessarily mean the number itself is negative, which is a bit weird to think about. And then lastly is the, lastly, lastly is the interquartile range. So if you've done general, I believe this gets covered, although not using integrals, obviously. But it's basically just going to be the distance between the 25th and the 75th percentile. So it basically just means solve both of those percentiles and then just do b minus a. That's pretty much it. So you do your integral equals 0.25, that's this one. You do your integral equals 0.75, that's that one. And then you just do 8 over 5 minus 8 over 7. That gets you your interquartile range. It's a pretty easy calculation, at least, yeah, as far as how that all works. What it actually means is, so if I go and redraw another sort of diagram, if I draw another little bell curve looking thing, then the interquartile range would be something like this. So between the 75th and 25th percentiles would mean that this is like 50% of the total area. That's what you're finding. The upper and lower bound that contains 50% of the total area. That's it for the lecture stuff there. So is there anything of what I've covered that you want me to clarify in any more detail? A second to have a think about it while I pull up some questions. Cool. All right. From the top, show that the function is a probability density function. I know it was the first thing we looked at, so it's been a bit, but does anyone remember the criteria for a probability density function? There's two criteria that you need to meet. One is that the function is positive. Oh, sorry, you're gonna say?
I was gonna ask if one of the criteria is just because there's a domain on the function.
One of the criteria is that there's a domain. Not necessarily, actually. Domain is likely to be the case, but there's actually some that don't have a... In fact, do I have one here? I think it was the percentile one that was like 90th percentile. Oh, I've gone too far. Let me see if I can find that. Where'd it go? Ah, no, it still does. Okay, yeah, so it's going to have a domain. But basically what you want to do is there's two criteria you need to meet. One is that the total area under the curve is 1, and the other is that the entire function has to be above the x-axis because you want all your probabilities to be positive. And so yeah, a lot of the time you'll have to have a restriction on your domain to achieve that, but some functions do just natively have, well, no, maybe I'm just wrong about that. I think you'll always have a domain, but the domain has to be chosen in a way where the total area under it equals 1. So that gives us a pretty targeted thing to achieve. First would be, is this function positive over its entire domain? It's 24 over x cubed, pretty tough to imagine what that is if you haven't seen or haven't thought about how to handle these kinds of things before. Does anyone know roughly what the shape would be? Like if you just ignore the domain for now. It actually ends up looking like a hyperbola. That's true of any odd n that's on here. So n equals 1, you have hyperbola. N equals 3, you have a steeper hyperbola. 5, 7, 9, all your odd numbers just make it steeper and steeper as far as hyperbola goes. It's worth playing around that a little bit just so you can see how to handle these other functions that aren't necessarily required for you to sketch, but definitely helps as far as proving things. Now, this might look like it's pretty bad for a probability density function until you realize that the domain is actually from 3 to 6. So we don't actually care about this negative portion here. We just want to make sure that this area is equal to 1. So how can we prove that that's equal to 1? How do we find area under a curve in general?
Do we do the definite integral?
There you go, definite integral. Nice. So definite integral 24 over x cubed. We're going to do it from 3 to 6. And as long as this equals 1, we're golden, because we want that whole area to equal 1. So, bit of revision. How do we antidiff this? That's going to be step 1 of doing our definite integral.
Chris, do we convert to a negative power?
Yeah, that could make life a little bit easier. So you go 3 to 6, but now you're doing 24x negative 3. And then even though it doesn't like technically do anything, it does make it easier to see how that would now antidiff. Would it be negative 12 on x squared? Probably. Let's find out. So capital F of x, power goes up, so you're now doing x negative 2, and then that power goes down the front, so 24 on negative 2. And so finally you've got negative 12 on x squared. Yeah, smashed it. Nicely done. So that's your capital F of x sorted. Step 1 of doing definite integral. What's the next step?
Do we have to sub in the value of the domain?
Yeah, gotta sub in that domain. Absolutely. What order do you do it in? So capital F of what minus capital F of what?
Is it capital F of 6
Yeah,
minus F of 3?
that's it. Nice. Very good. Yeah, everyone gets it back to front a lot of the time, so it's good that it's worth pointing out every time I do it. Top, take, bottom. Yeah, okay, and then we just sub those values in. It's nothing too crazy. Literally just algebra at this point. 6 squared minus 12 on 3 squared. 6 to 36, so minus 12 on 36. Minus and minus are going to make a plus. 12 on 9. So you got negative 1 on 3 plus 12 on 9 is 4 on 3. And then obviously the 4 and the minus 1 cancel down to just 3 over 3, which is 1, which is what we wanted to have happen. Nice. Okay. Part 2 is a slight variant on that. You don't actually do anything different. Is it even worth discussing? Yeah. Can someone tell me, if they can see it for question 2, what's the slight difference that you have to do in the procedure?
We need to find K.
Yeah, we need to find k. So you'll do the same thing, which is anti-diff your function. You'll still do capital F of 2 minus capital F of 0, but now you're going to force it to equal 1, and you're just going to rearrange for k. Does anyone want to see that happen live? Or should we move on to 3b?
Chris, can we do that live, please?
Sure can. Yeah. Okay, so first up, definite integral from 0 to 2 of x squared plus kx plus 1. So, got to get our capital F of x. What's that going to look like?
Chris, is it x to the power 3 plus kx squared plus x?
You're doing a lot of it good.
Oh no, hold on, no,
One of
never
it
mind.
got missed.
Wait, no, hold on. I think the first one is 2x.
Well, 2x would make it a diff, so it will go like 2 at the front and then raise down by 1. You're right to raise it up, but what you got to do then is divide through by that raised power. So when you bring it up to a 3, now you've got to go a third. When you bring it up to 2, you now got to do a half. The easy way to know whether or not you've done your anti-diff right, or at least double check it, is if you diff this, do you get back to where you started? And diff is where you bring the power down the front, reduce it by 1. So if you imagine putting this 3 back down and reducing it down to 2, you do get back to x squared. You do get back to, oh, sorry, this should say a k.
Chris, when we're doing our like solving, do we need to like show for C?
And not if it's definite integral. No. If you want to be like really safe, yeah, put a plus c in there. Doesn't really take much effort to do it. But for definite integral, they only really care. Like this one here just said, determine k. Whatever you do to get there, as long as you're showing like the overall arching steps, which would be anti-diff your function, sub in the terminals, make it equal 1, then that's all that really matters. But if you want to be safe, yeah, chuck a plus c in there. That's fine. I will say though, when you do your capital F of 2 minus capital F of 0, every single textbook out there will not put a c in this equation, which is why you'll probably not see this in this statement. It's not wrong to have it there, it just usually gets left off. Yeah, the only thing that we didn't do was make this equal 1. So we know for a fact that over this full domain it equals 1 because you want it to make it, you want to make it a density function. So you're going to have a third 2 cubed plus k on 2 squared plus 2. That's the capital F of 2. And then minus capital F of 0. I could write it out, but, you know, put a 0 there, 0 there, 0 there. The whole thing is just going to be 0. That equals 1. And then, yeah, just simplify. So 2, 4, 8. So 8 on 3. 2, 2, and then 2. So it gets back to 2. 2k plus 2 equals 1. 8 on 3 plus 2k equals minus 1. 2k equals minus 3 on 3 minus 8 on 3. 2k equals 8, 11 minus 11 on 3. K equals minus 11 on 6. So this one won't equal 1. This is a k value, not an area value, which makes it a bit harder to prove that you've done this right. You can do it, but it's a massive waste of time, because if you put in your k value in this spot and then do this whole thing again and see if you equal 1, that's a lot to prove an answer. So usually Usually you just take this as it comes, and then move on to other marks. Very hard to, well, very time consuming to prove if you got it right. Cool. Okay. So that's that one. Next one of interest would be to do 3b. So that's where you find the probability that x is less than 0.5. I'll start writing out the function. In the meantime, can someone tell me what we might do to achieve it? Even if it's just overall steps. I mean, you can do the whole thing if you want. If you're getting stuck, let me know.
Chris, do we first distribute the 12x squared through the brackets?
Distribute 12x squared through the brackets. Yeah. Yeah. Why do you think we do that?
Because if we're gonna anti-diff it, I'm guessing, right?
Yeah.
Well, not guessing. Well, we will be anti-diffing it. So then it's gonna be easier to anti-diff like a fully solved
Mhm.
function than a simplified one.
Yeah, expanding this out is going to be basically required. I think there is a product rule type thing for integrals, although it's higher level than methods goes. I only think that. I don't remember necessarily. But yeah, expanding that out, good idea. Once we have that, what might we do from there?
We set up the integral with the domains.
Yeah, set up the integral. What's the domain for the integral?
So it's gonna be from 0 to 1. So 0 on the bottom, 1 on the top, I think.
Okay. I know why you've done that. Have a read again if we're doing 3b. Something about that's got to change.
So we're going from 0.5
Yeah.
to 0.
Yeah, 0 to 0.5, correct. Because you want to do everything less than 0.5, which makes 0.5 your upper bound. Then yeah, you just put your function in there, you do the anti-diff, you sub in the values, and whatever that equals is your target probability. That is just solving a definite integral. Does anyone want to see that happen again? Or happy to move on? Oh, hang on. How do we know which value to put first in the integral? Which value to put first? I'm not too sure what you mean by what value to put first. As in like... Oh, yeah, okay. So that's when it says less than 0.5. So if you think about a number line, you've got the whole domain is from 0 to 1. We're looking for less than 0.5, which means we want this here. Bigger number always goes up top, smaller number always goes on bottom. And so, because if you flip that order, then that's like reversing the terminals of an integral, and so that ends up giving you a negative result. It's like if we think about any type of definite integral, like if we're doing this kind of function and you want to find area from here to here, let's say this is 3 and this is 2, the bigger one always goes on top and the small one always goes on bottom. So same thing here. Bigger one is 0.5, smaller one is 0.
Chris, wouldn't we just do like wouldn't we just sub in 0.5? Because I think if you sub in 0 into the integral, it's just going to be 0.
Yeah, that's correct. If you sub in 0 into both of these, you get 0. So yeah, it's basically the same thing as just doing capital F of 0.5. I would still, in my working out, still write capital F of 0, and then when I expand it out, I just wouldn't bother with doing anything here. Just leave it as capital F of 0.5. Yeah. But yeah, you're right. It does effectively just end up being the same thing as just doing capital F of 0.5. Does anyone want to see that written out fully, or is conceptual fine here? If so, have a think of question 5b. Yeah, question 5b. Mainly this is just trying to get your ability to interpret a question in terms of a piecewise. Because obviously there's no piecewise here now to tell you things. This is now interpretation, which is much likely to appear on the actual, well, actually will appear on the tech active and the tech free, I think. Both have a decent chance of occurring. Chance. Probability. Haha.
Because for 5b, like I haven't gotten the answer, but it's a process we just like expand and then we set the domain from 5 to 7.
Yeah, correct. So expanding
And
because of the, what was that last part?
well, then we just once we've set up our integral to be between 5 and 7, we just find that integral.
Yeah, correct. So expanding, obviously, because you want to antidiff, and you can't really do that when there's product. Why did you pick 5 and 7? It is correct, but yeah, why did you pick 5 and 7?
Well, it says that the function given is for between 5 and 11 days. So regardless, we have to look at starting at 5 days,
Mhm.
and then obviously the question states that within 7 days. So
Yeah,
it has to be between 5 and 7.
correct. Yeah. So the key thing to really understand there is that days is your x-axis, and so that's why you're able to plug in those values the way they go. So a lot of doing a lot of doing continuous probability is figuring out, okay, whatever the quantity is that's being talked about is my x-axis, is my domain. Everything else is kind of whatever. Like if we talk broadly speaking about how you might solve part C, whether it's a continuous probability thing or not, you solve it the same, like, broad steps. Does this wording remind anyone of anything?
I don't remember the term for it, but I remember we were doing something like this in yesterday's class.
Yeah. Yeah, conditional probability is what it is. It's this whole thing. Where is it? This, where you do your little straight line for conditional probability. Keyword given is pretty much a dead giveaway that it's conditional probability. So this means within 7 days, so you want to do your 5 to 7 there, given after 5.5. So if I were to write out what that actually looks like as a probability statement, it would be very ugly, but it would look like this. Probability, so between 5 less than equal to x less than equal to 7, given greater than 5.5. So 5.5 less than x and then less than equal to upper bound of 11, because that's our maximum possible days. And so that is a big, nasty conditional probability thing. but still, it does end up just being the let's just call this A and B for simplicity. You do the A intersect B, and you divide by the B. So, does anyone remember how to get the intersection of intervals like this? Or even, maybe can someone just tell me what the intersection is? Not the probability, but the actual intersected interval itself. You just draw a number line. You draw each of these individual things, and then you just look for where they overlap. I know I drew a dark circle here. You can draw a white one if you want. That's fine. But in the context of continuous probability, whether it's equal to 5.5 or slightly above 5.5 doesn't actually matter, because there's no way you can do your integral any differently. You're still going to set this as 5.5. You can't do like 5.5.00000, so on and so forth. So yeah, whether there's a less than sign or a less than or equal to doesn't actually matter. So yeah, that means the intersection is just from 5.5 to 7. So you want to do 5.5 less than equal x less than equal 7 over the b one, which is 5.5. Whoops, that's not a 5. 5.5 less than equal to x less than equal to 11, which means two separate definite integrals, one from 5.5 to 7 and the other from 5.5 to 11. You do each of those and then perform a division. This would be a monster of a question to do by hand. Very likely, very, very likely, this will be a CAS thing. That, or they'd have to give you a lot of marks to work with, in which case you're actually happy because you're doing two things identically and then just doing a division, and it gives you a lot of marks. So you'd almost be happy to have this on a tech free because it gives so many marks if it would be there. But yeah, that's how that one works. That's pretty much it. Let's see, is there anything else crazy in this PDF? Sketch, evaluate K. Boundaries, interpretation, conditional probability. Yeah, we've covered all the key things, at least for 15A. If you're looking to do the statistic stuff, that's going to be in your 15B, mean and percentiles, and then in 15C, I believe, is your variance standard deviation. This is your big, nasty proof for how you can get the these properties things. So if you want them, you've got them there. If you want to scroll through that, have fun with it. Otherwise, not necessary. But okay, that's it for the lesson. If you want to stick around to get any questions answered, feel free. Otherwise, I'll leave it to it. No worries.